All right, students, let's try number 30 here from chapter 5. And it says this. This is the chapter on the universal law of gravity. Maybe I better put that in here that says, all right, if you have two masses, m1 and m2, over r squared, this would be the effect. Now, one subtlety in this is if you're on planet Earth here, and I was going to draw a person, but I'll just make a little blob here. Okay, so we got a little blob, a small distance above the surface of the Earth, and we say, okay, let's look at the tug here. It's easy to think of this as just two objects and say, okay, well, one object's the Earth, and so here's the center of the Earth, and the other object is this round thing, let's call it a basketball, and that basketball gets pulled down, and you think, okay, I just put those into that equation. It really is a bit more complicated than that. It really would be that, okay, here's your basketball, and I'll continue to think of the basketball as one object, although you could even break the basketball into sub-objects. But the Earth is a big object, so I'm going to break the Earth down into little pieces. Maybe there's basketball-size objects just under the surface of the Earth, and then maybe a layer below that are more basketball-size objects, and a third layer below that are more basketball objects. And if you think about what is happening here, it is really the basketball is getting pulled to each of these other basketball-size objects. And the truth is we could break this down molecule by molecule, but I think just down to basketball-size objects is good enough. And so if you added up all of these tugs, you would get the total effect of the Earth. In other words, I'm thinking of the Earth now not as a single object, but as a bunch of basketball-sized objects. And I would have to do this calculation between each of those basketball-sized objects. Now, here's the reason I say that. If you look at this problem number 30, it says you're steaming across the Atlantic Ocean on a large cruise ship. What would happen to your weight as the ship leaves the deep water of the North Atlantic and enters the shallow coastal waters of the United States? So let's maybe draw two pictures here. Here is the Earth and an object. And I know this problem says a person, but I'm just going to go with my basketball theme. And so let's say this is a basketball just above the surface of the Earth, so it's on a cruise ship, but it's over the deep part of the Atlantic Ocean. And so there's, landmass over here, and so say here's New York, and there's landmass over here, and so this is Europe. My favorite spelling of Europe. Europe. Okay, so there's New York, there's Europe, and between them is this big trench that's filled with water. All right, now, of course, water has mass, and so imagine a bunch of basketball-sized objects. They would mostly be water. And until you got pretty deep, then they would become rock, like the Earth, and eventually you'd get inside the Earth where it'd be magma. Now, if you compare that to, and so here's the basketball, and maybe now I'll draw the Earth, okay, and now you're really close to New York, and so here's New York, and New York, it's if you know anything about the oceanography here, the continental shelf sticks out pretty far on the east coast before it dips down into the deep waters of the Atlantic and then comes back up and makes the continental shelf in the continent of Europe. Okay? But again, if you think about a bunch of basketball-sized objects, most of these basketball-sized objects are then rock. They're not water. And that's the key to this problem, is because your total weight is going to be the tug of all of these basketball-sized objects. And your biggest effect, and you can see it back in the equation, are the ones that are closest to you because of R. And so this problem is trying to get you to see here that if you have rock underneath you compared to water underneath you, the closer objects, the objects that have the most effect of the tug, and remember, it's really all the basketball objects that make the tug, but again, the most significant ones are the ones directly underneath you. And of course, there is a lot of them that are not directly underneath you. And you have to add them all together. So there's only going to be a slight difference between something like this and like this, because again, you're adding so many of them, most of them are just rock. But there is a slight subtlety between these ones that are close, that are made out of water, and these that are close, that are made out of rock. And the ones that are rock have more mass, and so more mass at that same distance. Comparing the two is you would have a slightly greater tug. So you would actually weigh a little bit more. I don't think it would be enough that a human could notice it. That's why nobody really ever says, hey, I can tell we're getting close to land. We are in shallow water now because I feel heavier. Nobody says that. But the question is, what happens to your weight as the ship leaves the deep water and then gets to the shallow water? And so you're going to have a small increase. The density of rock is a couple times more than water. Of course, like I said, it won't be like you would weigh a couple times more. You would only be a little bit more because, again, just a very, very small percentage of all the stuff changed. Most of the Earth is still being the same. You know, all of this is the same tug as all of this. It's only the stuff that, you know, is the depth of the ocean that would change. And so each basketball size would change by a big percentage, but the number of basketballs within the ocean is small compared to the whole Earth. And so you would have a small increase. That's the bottom line here. That's what they're after in that one. Hope that helped.